Let's go ahead and finish up this section on vectors. Now, we've talked a little bit about vector. We talked about component form, horizontal components, vertical components. We've talked about IJ component form of vectors, where the horizontal component is the coefficient of I, vertical component is coefficient of J. We're going to go ahead and look at some applications of vectors in component form in this video. But let's go ahead and look at some notation that we've used before first, okay? Remember when we recently did polar and rectangular coordinates, we used quite a bit these two equations. X is equal to R times cosine theta, Y is equal to R times sine theta, where R is the radius and theta is the central angle, right? So if you had any circle centered around and you thought about any point, here's your radius, here's your angle theta, you could get your X value by the R cosine theta, you could get your Y value by the R sine theta. So those two things always held true. Now keep in mind what we just talked about with vectors, okay? Remember, we talked about something called magnitude. Magnitude of any vector V. Notation for that is the magnitude of V, okay? The bars around the V. What was this? This was the length of the vector. Look at that little diagram I did. I know it's kind of small, but imagine you have a vector. Remember, we don't know the initial point, the ending point, so we can imagine starting at 0. It would be the same vector as if you started anywhere in component form to your terminating point. Notice the length of that vector is the same as radius r when we were talking about coordinates with polar coordinates, okay? This is the same as our radius r that we did before. We found it by the square root of horizontal squared plus vertical squared, square root of a squared plus b squared as you went through. But magnitude is like the radius. So this, in this formula, we can really think about for any vector v, we can think of this as the magnitude of v. That's the same as our radius, right? Magnitude of v. X, when we think about our x value, look at our diagram. The x value, if you start at your initial point, your x value was your horizontal distance. That was our horizontal component. So our x value is our horizontal component. Our y value was our vertical distance. That was our vertical component. So our y value is our vertical component. This leads to formulas that we can use with vectors. They're actually the same formulas that we used back in the past section. Since x is equal to r cosine theta, we can always find the horizontal component of a vector by taking the magnitude of the vector, or the radius, times the cosine of that central angle. Now, the central angle is always when you start with your x-axis going to the right and then up to the vector itself. So that's how you would find your horizontal component. Your vertical component is going to be the magnitude of the vector times the sine of that central angle theta. These are always going to hold true. So if you know magnitude, length, and you can figure out, or you have your central angle theta, you can find horizontal and vertical component without knowing your endpoints absolutely every time. Same formulas that we used with polar coordinates. So put these in our toolbox. We're going to use them, okay? Let's go ahead, keep that in mind. So again, I'm going to go to a different page. So I've just rewritten horizontal component, magnitude times cosine of an angle, vertical component, magnitude times the sine of an angle. So what that means is when you think about component form, how did we write component forms? Our component forms for any vector v, we always wrote component form, horizontal component, vertical component. So this was our component form. What is horizontal component? It's magnitude times cosine. So you can always get that by magnitude times cosine of a central angle. Vertical component, magnitude times sine, sine of the central angle. Think about ordered pairs. When you did ordered pairs, you had XY values. Remember when we started talking about unit circle and all of that? X's corresponded to cosine in some way, Y's corresponded to sine in some way. So same type of thing. Horizontal always goes with cosines. Vertical always goes with sines. And it's the same thing if you're doing the IJ component form of one. You have your horizontal component, which is magnitude times cosine of the angle, I. Vertical component is magnitude times sine of the angle, J. So we can write our components in these different ways. Example 19 and 20 from our notes. If we look at this, we want to find our horizontal and vertical components of some vector v given magnitude of the vector, or the length of the vector, is 800, and the central angle is 135 degrees. This is giving us the direction of the angle. The 135 is telling us what we have going on. Now, you don't have to sketch these. I'm going to sketch this in just so we get a feel. Remember, you can start at any point, right? So I'm going to go ahead and just look at this as if I were starting at 0, 0. So if you were starting at the origin 0, 0, okay, think about our circles. This standard position is to the right, is to the right on our x-axis. Here's our y-axis, okay? To get to the terminating side, we have an angle of 135 degrees. Now, remember earlier in trig, 135 degrees is over here, okay? This angle is 135 degrees. So starting at the standard position, if we go a direction of 135 degrees, our vector is going to be going up and to the left. This is our vector. And the length of that vector, so this is our vector v, and the length of that vector is 800. Okay? So right here's our vector. Central angle theta tells us the direction. So we know that's how we get that. We want the horizontal and vertical components. Well, the horizontal component of any vector can always be found by the length of the vector times the cosine of that central angle. So for this problem, that's 800 times the cosine of that central angle, which is 135 degrees. Now, if you're dealing with one of your nice angles, the ones like we learned from the unit circle, it's always great to be exact when at all possible. So I know that the cosine of 135, I'm in quadrant 2. Cosine's negative in quadrant 2, so that's going to be a negative. The 135 degree angle has a cosine of root 2 over 2. So we have a cosine of 135 is negative square root of 2 over 2 times 800. And I'll multiply these. 800 times negative root 2 over 2 is a negative 400 square root of 2. So my horizontal component is a negative 400 square root of 2, okay? We need our vertical component. Vertical component is the magnitude times the sine of the angle. So that's going to be 800 times the sine of 135 degrees. If you're going back and up, that's kind of like going into the second quadrant. Sines are positive there. So that's going to be 800 times the sine of 135. Sine of 135 is positive root 2 over 2. 800 times square root of 2 over 2 is 400 times the square root of 2, because 2 will go into 800 400 times. That's what I did in both of those. So my vertical component is a positive 400 root 2. So in component form, this problem would be either negative 400 root 2, positive 400 root 2 written this way, okay? Or I would write vector v as negative 400 square root of 2i, too hard to mix up the I and j, be careful, I, plus 400 square root of 2j. Those are both the vector. We know the horizontal component, we know vertical component. So we know the vectors in both component and ij component form. So we can write them in those ways. Make sure your angle is the central angle, meaning starting in that standard position. There are times when we're going to have to manipulate some things to get the theta so that we can use this, okay? But we can always take magnitude times cosine and sine to get our components of our vectors, okay? Try number 20. Okay, let's look at number 20. We want to find horizontal and vertical component with this given, when we're given the magnitude. So we're told that our magnitude of vector W is 350. And our central angle, our direction, is 210 degrees. You do not have to sketch this. The only reason I'm doing the sketches is to illustrate, okay? So imagine if you started any vector at the origin. If you have a direction of 210 degrees, starting with your standard position, if you go 210 degrees, to the other side of the x-axis is 180, 210 is right here. So there's our 210 degrees. Notice third quadrant, we're going back and down. Think about this. Vector ends in quadrant 2. What do ordered pairs in quadrant 2 look like? Negative, then positive. We should have a negative horizontal component, a positive vertical component. What did I have in my answer? Negative horizontal component, positive vertical component. Now look at this one. We're ending in quadrant 3. What do ordered pairs look like? Negative x's and negative y's. We should have a negative horizontal component and a negative vertical component. Let's see if we do, okay? My horizontal component is going to be the magnitude of the vector times the cosine of the angle. So that's 350 times the cosine of 210 degrees. Now, this is one of our nice angles. 210 degree angle has a terminating point where the x value is negative root 3 over 2. So this will be negative square root of 3 over 2 times 350. 2 will go into 350 175 times. Positive times negative is negative. So that's negative 175 square root of 3. That's our horizontal component. Okay, vertical component is going to be magnitude times the sine of the angle. Magnitude is 350 times the sine of 210 degrees. Sine of 210 degrees is a negative 1/2. Positive times negative is negative. 350 times 1/2 is 175. Vertical component. So notice W in component form has a horizontal component of negative 175 root 3 and a vertical component of negative 175. So we can write it that way, or we could say negative 175 square root of 3i minus 175j. Same thing, component form, ij component form. Notice negative horizontal component, negative vertical component. That should always happen. Okay. Go ahead and pause the video and try number 21 and 22. You're given your magnitude, you're given your angle. Okay. Now, I'm going to go ahead. I'm going to write down my answers in the IJ component form, but I'll show the work. For this one, vector U should be the vector 230I plus 230 square root of 3j. Vector V here should end up being negative 60I minus 60 square root of 3j. Those are my answers. If you got those right, great. Go ahead and move on with the video. Otherwise, I am going to show the work. Our horizontal component is the magnitude of the vector times the cosine of the angle. The magnitude of the vector was 460 times the cosine of the angle is cosine of 60 degrees. Cosine at 60 degrees is 1/2. That's 460 times 1/2. That's a positive 230. Okay, that's our horizontal component. To the right, 230 units is what that means. Our vertical component is magnitude times the sine of the angle. At 60 degrees, the sine of the angle, okay, is square root of 3 over 2, positive square root of 3 over 2. We're in quadrant 1 at 60 degrees. 2 will go into 460, 230 times. We still have the square root of 3. So my vertical component is 230 times square root of 3. So there's my horizontal component I, vertical component J. There's our answer. Okay. Be careful if the angles are changed up a little bit. Remember that negative 120 degrees is coterminal with, if you look at this, this is coterminal. If you go 360 around, that's at the 240 degree angle, okay? Or you can look at it graphically. Negative 120, this would be negative 90, negative 120 would be right here, okay? As a reference angle of 60 degrees here, okay, in quadrant 3. But we're terminating in quadrant 3. That means we should have a negative horizontal component, negative vertical component. Look at my answers, I did. Horizontal component is going to be magnitude times cosine of the angle. So that would be 120 times the cosine of negative 120 degrees, or cosine of 240 degrees if you want to get coterminal angles first. But the cosine of negative 120 is negative 1/2. 120 times negative 1/2 is a negative 60. Horizontal component is negative 60. Okay. Vertical component is magnitude times the sine of the angle. So 120 times the sine of negative 120 degrees. The sine at negative 120, your reference angle is 60 degrees. The sine at anything with a reference angle of 60 degrees is root 3 over 2, but we're in quadrant 3, so that's a negative root 3 over 2. So that is a negative 60 square root of 3. There's your vertical component. Okay? So that's your vector. Vector V. All right? These guys right here, using that idea that horizontal component, well, right here, I'll just box it in. Horizontal component is always magnitude times cosine of the angle. Vertical is always magnitude times sine of the angle. These are great when we know magnitude and we know direction. So here's where the big applications come in for vectors. All right, let's move on. Real world problems. I have two types of examples I'm going to look at here. As far as some things go on. Excuse me. First of all, let's talk about things called velocity vectors. Now, lots of times when you are dealing with airplanes, think about the towers at airports and all that equipment they look at and all of those things they look at, airplanes in the cockpit, all the little things they look at. lots of times they're seeing vectors, they're velocity vectors. When you have an object, such as a jet, moving at a certain speed in a certain direction, a certain trajectory, we can represent this using a vector, a velocity vector, because it has a speed, it has a direction. We represent with velocity vectors, the magnitude is the speed of the object. How fast is it moving? Think about that. If an object is moving really fast, the length of distance it covers is going to be more. If it's going really slow, the length of the distance it covers is shorter. Speed affects length. Our magnitude is the speed of the vector. And the angle represents the direction of the object, I'll say relative to the ground. Think about standard position. Remember, our direction angle theta started to the right, like the x-axis to the right. Let's look at this situation in this example. We have a jet that's flying north 20 degrees east at a speed of 500 miles per hour. We want to find both the horizontal and vertical components for this and represent this jet using a velocity vector. Well, let's look at the information we're given. Think about what north 20 degrees east means. This is when we talk about bearings or headings. It's giving us the direction, but we're always starting from north or south and then going east and west. So imagine going north to the east. North is up and down, is up, east is to the right. So we're going north 20 degrees east. That would be this little angle here, 20 degrees. So to the north, 20 degrees east. That's not our central angle. If you imagine your x and y axis here, like we did before, central angle, the theta, the direction angle theta, is the distance from the x-axis to the vector. This is our vector that's representing the trajectory of that jet. How can we get it? Well, this is a 90-degree angle. We know this little bit's 20, so this will be 90 degrees minus 20 degrees, which is 70 degrees. So north 20 degrees east corresponds to a direction angle or a central angle of 70 degrees, okay? Also remember that with velocity vectors, magnitude is the speed of the vector, speed of the object. We know the speed of the object is 500 miles per hour. So I'm going to let v equal the vector. So that means the magnitude of the vector is equal to the speed of 500. So I know magnitude and I know direction. So since I have those, I can find my horizontal and vertical components. Remember, horizontal component is the magnitude of the object times the cosine of the central angle. That's going to be 500 times the cosine of 70 degrees. Now, unlike the last few examples we did, we had nice angles, 60 degrees, 120 degrees, 135 degrees. This is not a nice angle. So in exact form, this is what we would have. But in applications, we really want to have an idea of what this is. So go ahead, make sure your calculator is in degree mode, okay? And do the calculation. If you go 500 times the cosine of 70 degrees, you should get a 171.01007. It goes on forever. Remember, that was in degrees. It had to be degree mode, okay? If you're in software or you're on a test or something, you'll be told where to round. Let's go ahead and round to the 10th. So that would be approximately 171.0. Our horizontal component is approximately 171.0. Okay. This is the distance left to right. Our distance is being given in miles. So what this means is from wherever the jet is starting, the initial point where we start doing it, Horizontally, it's covering 171 miles roughly. That's what that's referring to. Vertical component is the magnitude of the vector times the sine of the angle. So that would be 500 times the sine of 70 degrees. Now keep in mind, with a 70-degree angle, we're going to the right and up. We're going eastward and northward. Those are both considered positive directions. These should be positive values. And if you do 500 times sine of 70 degrees, you're going to end up with a 469.846. It goes on. So again, I'm going to go to the 10th. That's approximately 469.8. Okay. So my vertical component is approximately 469.8. Okay. All right. Basically, what that means is for a single hour of time that this jet's flying, it's flying 500 miles an hour. So its distance this way in 1 hour would be 500 miles. Its horizontal distance would be about 171 miles. Its vertical distance would be about 469.8 miles. We're going to the right, eastward, and up northward. This is our vector, and we could write it as 171.0i plus 469.8j. We could also use component form, but that's the velocity vector for our jet. Now keep in mind, if you are going north, that would be considered a positive direction. South would be considered a negative direction. East is a positive direction. West would be considered a negative direction. So the fact that we had a positive horizontal component means that we're really going northerly. This would be a northern component if we were thinking north-south. Sorry, horizontal, left, right, easterly, east direction, eastern component. Sorry. I'm so used to thinking rise and run north-south versus east-west first, and I wrote it differently. Vertical component is a positive. Vertical is up and down, so that's positive means more north. So this would be my northern component. Vertical, up, down, okay? All right. So there's an example. Let's look at another. Go ahead and pause the video and try this one. It's just like the last one as far as setup. Jet flies north 35 degrees west at 560 miles per hour. We want to find the velocity vector v for this jet. We're going to round the components to the nearest tenth. The answer you get for this, if you round to the 10th, you should end up with the vector v being approximately negative 321.2i plus 458.7j. If you got that, fantastic. Go ahead and move on. I'm going to show the work here for this. So we're going north 35 degrees west. What does that mean about our direction angle or our central angle? Think about what this means. We're going north, so from wherever the jet's starting, it's going to the northwest. West is to the left. So we're going up and to the left, an angle of 35 degrees. That's what that's giving you. North and to the west, up and to the left, that angle is 35 degrees. We want our angle theta. Theta is the angle from the standard position all the way over to the vector, to the jet, okay? Well, first quadrant is made up of 90 degrees, then we have an additional 35. So this is going to be 90 degrees plus 35 degrees. That's 125 degrees. That's our direction angle theta. Remember that speed is the magnitude. So the magnitude of this vector is 560. Basically, it's giving you the length of the vector. In an hour, it's going to cover 560 miles. That's the length of the vector. So as we go through, we need our components. Our horizontal component is going to be the magnitude of the vector times the cosine of the angle. So that's going to be 560 times the cosine of 125 degrees. Cosine of 125, since we're to the left of the origin, we're going in the back direction, west. This should be a negative number. We're going west. This should be negative. So grab your calculator, go 560 times 125 degrees. We should end up with, to a single decimal point, approximately negative 321.2. Negative direction, backwards. We're going westward. Negative 321.2 miles. That's what that's referring to. Vertical component, magnitude times sine of the angle. So 560 times the sine of 125 degrees. Well, we're going northward. That should be a positive. If you went 560 times sine of 125 degrees, you should get approximately 458.7 positive. We're going upward. Notice we're going northward. Okay. We have a northern component of 458.7 miles. We have a westward component of negative 321.2 miles. That just means going west 321.2 miles. And so that's our vector. Horizontal component I plus vertical component J. Okay. So east and north is positive, west and south is negative. All right. Let's look at the next one. Sometimes we may know the components, but we don't know the angle. In the last couple of examples, we knew the angle, we knew the magnitude, and we were finding the components. Sometimes we need to figure out the angle. This is just like what we've done in the past in first couple units. Well, when we first started talking about tangent, if we were looking for an angle, we could use the idea that tangent is opposite over adjacent, okay? We have that idea as we go through. Imagine for any vector v, I could sketch in horizontal component and vertical component, and I'm looking for that angle theta. Well, if I'm in quadrant 1, like I am here, think about how you can get theta. Remember, tangent of theta is always opposite over adjacent, or it's your y value over your x value, as long as x is not 0. You can't divide by 0. As long as your horizontal component is not 0. In this diagram, what is the opposite? The opposite is my vertical component. So tangent of theta is my vertical component over my adjacent side, which is my horizontal component. And when we were looking for angles, what did we use? We used inverse trig functions. That means for quadrant 1, that theta is going to be the inverse tangent of the vertical component over horizontal component. Anytime you're looking for the angle and you know components, you can use inverse tangent to get there. Now be careful, inverse tangent was only defined for quadrants 4 and quadrants 1. So when you evaluate inverse tangent, it's really going to be giving you the reference angle. You have to consider which direction you're going, which quadrant you're in, to get what the actual central angle theta is. Let's look at this problem right here. Direction and magnitude of the vector in component form, negative 4, 7. So notice, our horizontal component is negative 4. Our vertical component is a positive 7. What does that mean? Horizontal component negative means we're going to the left, vertical component's positive, and up. If we imagined this diagram, we're going to the left and up. Our vector has that shape, that direction and shape in some way. So when we think about wanting our theta, we're actually looking for this angle right here, okay? We can use inverse tangent to get there. So let's look first of all. Inverse tangent of vertical component over horizontal component, opposite over adjacent, y over x, would be the inverse tangent of vertical component is 7, horizontal component's -4. So that's the inverse tangent of a -7/4. Inverse tangent of -7/4. Now, that's not one of our nice values. We don't have, for any of our nice angles, we don't get a tangent of -7/4. So I'm going to go ahead and use my calculator. We're going to stick with degree mode here. I'm going to go ahead and look at degree mode. So this is a -60.255, and it goes on. Remember, inverse trig functions are angles. So this is degrees. So -60.2555 degrees. Well, what is that? That's actually giving us, if we were to look at the diagram, that's actually giving us this angle right here, the -60.255 such and such degrees. That's really giving us that there. It's giving you your reference angle. That means your reference angle here is about 60.255 degrees. We want to know theta. Notice if you put theta with that 60 degrees, you would get a full line, which is 180 degrees. So you can get this central angle theta by taking the 180 degrees minus that 60.255 goes on. So our theta is actually approximately 109.7 degrees. That is our central angle theta, okay? That's the direction. This is the direction of vector u. That's the direction of vector u, okay? If you wanted to think of it as bearings or headings, remember when you think bearing or heading, the north, south, east, west, what's happening with this vector? It's going up and to the left. So it's going north to the west. So I could write this as north something west. The degrees that go in there, you're wanting this little bit. How far from the north to the west am I going? If you look at that, you know you have a 90 degree here. So if I went the whole angle, 119.7, and I took away the right angle portion of it, okay? And I took away that right angle portion of it, what would I have? 29.7? That would be north 29.7 degrees west. Those would be headings. That's another way you can talk about direction. So you can do it in northeast, southwest, or you can do it in the actual central angle that you go through. Let's revisit that first jet. Just have a couple more examples here. In our very first example with the jets, we had a jet that was flying north 20 degrees east at 500 miles per hour. Now, so for that jet, we had a velocity vector, okay, of v equals 171.0 I plus 469.8 J. Imagine what's going on. Again, you do not have to have a sketch here, but just look what's going on. Horizontal component is positive, vertical component is positive. We were going northeast. So the jet from wherever it starts is going northeast at about 20 degrees. That is our velocity vector for the jet. So that's our jet's direction, okay? Now let's throw something else into it. always make it a little more complicated, right? Think about this. If you're flying to Chicago, you can take the exact same plane, fly at the exact same time of day, in the exact same path to get there, and you're going to end up getting there in, I have no idea how long it takes to fly to Chicago. I should have looked it up. You might get there 1.5 hours one day. You might get there in 2 hours the next. But you did it at the same time. What's the difference? If the wind is perfectly still, there's no wind at all, then the time it takes to get there is based on what the jet can do on its own. But if there's a wind, it can either hinder or help you, right? You could have a tailwind where it's kind of pushing you and making you go faster. You can be heading into a wind, kind of fighting the wind, which is going to slow you down. You could have a crosswind that's going to throw you off course, okay? So imagine that we had a crosswind of 65 miles per hour heading northwest. So what's happening is you have the wind blowing northwest at 30 degrees. What would northwest look like? Up and to the left. That's up to the left, about 30 degrees. That'd be like that, about like that, okay? So you have this wind that's heading up and to the left at an angle of 30 degrees, maybe a little more than 30 there. But what's going to happen to the plane, do you think? Imagine. What might happen to the jet? That wind is pushing against the plane this way. It might throw it off course, right? Might throw it off course, make it go a little more to the west as it goes that direction. Makes sense? There's an effect of a crosswind, okay? So when we look at a problem like this, what we want to do is find the actual or the true direction and speed of the jet. This takes into consideration what happens because of the wind. So that's taking in consideration the wind. We are going to come up with a vector for this called the resultant vector. What is the resulting outcome? What's going to happen after the wind pushes it off course? What is its actual direction and speed at that point, okay? In order to do that, I'm going to have to do a couple of things here. First of all, I need to know a vector for what's happening with the wind. I need a velocity vector for the wind. So I'm going to let W be the vector for the wind. Now, how do I get the horizontal component? I take the magnitude of the wind times the cosine of its central angle. Well, if it's going north 30 degrees west, that's a central angle of 90 plus 30. That's 120 degrees. So north 30 degrees west is the same thing as a theta, or central angle, direction angle, of 120 degrees. So I'm going to have the speed was 65 times the cosine of 120 degrees. Cosine of 120 degrees is a -1/2. 65 times -1/2 gives us a -65/2. So my horizontal component is -65/2. Vertical component is magnitude times sine of the angle. Magnitude is 65. Cosine of 120 degrees. So that's 65 times positive square root of 3/2. So I'm just going to write that as a 65 root 3/2. That's my vertical component. So my wind is negative 65 halves I plus 65 square root of 3 over 2j. There's my velocity vector for wind. Here's my velocity vector for the jet. So we have our jet and the wind, okay? The resulting vector is what happens when you add what's happening to both. You take what's happening with the jet itself, and then you factor in, you add in what's happening with the wind. So the resulting vector, the resultant vector, is going to be what happens when you add these two vectors together. Think about what we did with vector addition, okay? So we have 171.0I plus 469.8J minus 65 halves I plus 65 square root of 3 over 2J. When you do vector addition, you add like components. So we'll have 171.0 minus 65 halves. I'm going to go ahead and evaluate that. 171.0 minus 65 halves is approximately 138.5 I. Then we're going to deal with the J's. 469.8 plus 65 root 3 over 2. I always try to leave it in exact form until the final answer as much as possible. So evaluate that. That's a positive 526.1J. So our resultant vector, V plus W, is 138.5I plus 526.1J. What's happening? The jet on its own fuel, the jet without any wind at all, in an hour can go 171 miles east, positive, so east, and 469.8 miles north. But when the wind came in, now the jet is actually only going 138.5 miles east, but it's going 526.1 miles north. It's going further north, but not as far east. That makes sense with the wind. The wind is pushing that vector up this way a little bit. So it's not going as far east, but the wind is kind of coming in from under it, so it is speeding it up a little bit. This down here is what we call the resultant vector, or the true actual vector representing what's happening with the plane. But what did the problem ask for? This is the resultant vector. But go back to what the problem asked for, okay? If we look in the problem, now what I wrote down here, I did not have it. What if we wanted to know what is the actual speed of the jet and the actual heading of the jet? What's its direction? What's its speed? So what we need is we need the magnitude, and we need our headings, northeast, southwest. Now I know I'm going up and to the right, positive horizontal component, positive vertical component, so I'm going north and east. So my heading is going to be northeast, but I need the angle, I need the magnitude. Let's finish it up. If we know a vector, we can get that. So for V plus W, my resulting vector, I need the magnitude. That's going to be the magnitude of V plus W. Remember, V plus W we found to be approximately 138.5I plus 526.1J. So magnitude would be the square root, horizontal component squared, plus vertical component squared, okay? So we go in, plug that in, horizontal component squared plus vertical component squared. Okay. Go ahead. See what's happening with that. You know what? I did not grab. Usually I already have that worked out there. Okay, magnitude. If you do all of that, you should get approximately 544.0. So that's speed. Now direction. Remember, we start with direction. We want to get our theta. So to get that, first thing we're going to do is take inverse tangent of vertical component over horizontal component, opposite over adjacent. So that's inverse tangent. Horizontal component is 526.1. Vertical component is 526.1. Horizontal component is 138.5. So we find our inverse tangent. Now, if I round to the nearest tenth, that's 75.3. Remember, this is an angle, that's degrees. Now, inverse tangent is always in quadrant 2 or quadrant 1. So positive 75.3 degrees means it's giving us this angle here. Okay? Isn't that what we want for our theta? Our theta is from standard position up. So this actually is theta. Our theta is 75.3 degrees. So we know theta, we know speed. It just depends on what you want. So the jet, with the wind in consideration, has a speed of approximately 544 miles per hour with a direction of 75.3 degrees. Now, if you want the heading or the bearings, notice these problems were given northeast, northwest, things like that. We really want the heading or the bearings here, the heading of the jet. We know it's going north and east. So we know it's going north and east. We need to know what this angle is, the angle between the north to the east. We need that. We know this little itty bitty one's 75.3. So how can we get that? We can go 90 degrees minus 75.3 degrees. That's 14.7 degrees. North, 14.7 degrees east is the same as a direction angle of 75.3 degrees. Okay, so we know the speed, we know the direction. Anytime you have two forces or acting on one object, so in this case it was the jet itself and then the wind acting on the jet. Whenever you have those things going on, you can deal with resultant vectors. Resultant vectors deal with adding those two forces together. Okay, let's look at one last example here. Now, this is actually very similar to the jet type problem, except you could think of tugboats, things pulling, two different tugboats pulling on one object. What would be the result of it? Two different forces acting on one object. What would be the result of it? Let's look at this one. If you want, go ahead and pause the video, try it out, try to set it up. It's kind of like with velocity vectors. Instead of magnitude being speed, magnitude is the force that's put on the object, okay? We have two forces. We have a force of 50 pounds and a force of 75 pounds that are acting on an object centered at the origin with angles of 60 degrees and negative 30 degrees. So what's happening is, imagine a graph, okay? Here's our object. So right there's our object, okay? We have two things happening. We have an angle of 60 degrees. So 60 degrees goes this direction, right? So we have an angle, a force of this direction going against the object, pushing the object, okay? With a force, a weight of 50 pounds, okay? Then we have another force. Think about what negative 30 degrees is. Negative 30 degrees is like this. So we actually have another coming down like this, negative 30 degrees, acting on that object with a force of 75 pounds. Now, this one has a bigger force than this one, so it should have a little bit more of an effect than this one, okay? But that object's being moved this direction and this direction. What's the result of that? It's very similar to what we did before. And what I'm going to do is I'm going to come up with a vector for each one. So the first force, okay, is 50 pounds at an angle of 60 degrees. Okay, I can come up with a vector for this. So I'm going to let V be this vector. And I can get my horizontal component. Same type of thing. Magnitude with speed with force. I'm going to let magnitude be force. I'm going to take the magnitude of the vector times cosine of the angle. That's going to be 50 times the cosine of 60 degrees. That's 50 times cosine of 60 is 1/2. So that's 25. My vertical component is going to be magnitude times sine of the angle. So that's going to be 50 times the sine of 60 degrees. The sine of 60 degrees is square root of 3 over 2. That's 25 times square root of 3. So this vector can be represented by 25i plus 25 root 3j. So I have this guy. That's one force, okay? I'm going to do the same thing for the other force. I'll let that one be W. You can use F1, F2. I think the book might do that some as far as we go. So let's look at the second force. So our second force is 75 pounds being pushed against it at an angle of negative 30 degrees. Okay. So what's happening here? Our horizontal component is going to be the force of the vector times the cosine of that central angle. That's going to be 75 times the cosine of negative 30 degrees. That's 75 times cosine of negative 30 degrees is a positive square root of 3 over 2. So this is a 75 square root of 3 over 2 horizontal component. Vertical component is going to be the magnitude times the sine of the angle. So that's 75 times the sine of negative 30 degrees. That's going to be 75 times a negative 1/2. That's a negative 75 halves. Okay. So our second force is represented by 75 root 3 over 2i minus 75 halves j. So we have something representing each force. If both forces are acting together at the same time on that one object, what is the result? So this is like what we did. Let me move this for a second. Excuse me. Make a little more room here. So what we want to see is, what is the end result? What is the end result on the object? How is it being displaced by both forces acting on it? Well, that would be another example of a resultant vector, and that's going to be V plus W. So we have 25i plus 25 root 3j plus the 75 root 3 over 2i minus 75 halves j. Remember, when you do your addition, you add like components. So 25 plus this, that would be 25 plus 75 root 3 over 2i. Then deal with your j's, plus 25 root 3 minus 75 halves j. This would be my resultant vector, the sum of the two. Okay. And it all depends on what you want in the end, if you want an exact form or if you want as an approximate form. We usually do approximate. Let me go to the 100th here. So that means V plus W is approximately 89.95I plus 5.80J. This is the result. So what's happening? What is my result of those two forces acting on that one object? That one object is being displaced horizontally. Remember, that's your horizontal component, displaced a distance of about 89.95, and vertical component's positive, just up a little bit, 5.80. That object has actually been displaced to the right 89.95 and up by 0.50, with both of those forces acting on it for a set period of time. Okay, that's what's happened. Now, what the problem wanted is, it first says find the magnitude and direction. So this is the resultant vector. This is our resultant force. The problem asked, what's the magnitude of the resultant force? Well, remember, magnitude, the resultant force is the sum, is the square root of your horizontal component squared plus your vertical component squared. So that's going to be square root of 89.95 squared plus 5.80 squared. If you go through and evaluate that, you should get approximately 90.14. The force was given in pounds. So the magnitude of the resultant force was 90.14 pounds. That was our magnitude. And if we want to know the direction, our theta, that's where we use inverse tangent. Inverse tangent of vertical component over horizontal component is going to be inverse tangent of 5.80 over 89.95. If you do that, you get approximately a positive 3.69. That's an angle, so it's degrees. Now remember, inverse tangent only puts you in quadrant 1 or 2. So that's right here, that 3.69 degrees. Notice when I did that sketch a minute ago, 89.95 to the right and up, that is a teeny little angle there. That's that angle, and that is our central angle. So we have the direction and we have the magnitude, okay? This problem actually had one last question, and this is it for this section in this video. Look at this last question. Okay. Find the equilibrium force needed to keep the system at equilibrium. System at equilibrium. Notice the object started nice and centered at the origin. Keeping it at equilibrium is keeping that balance. We want the resultant force to be 0. Resultant force is a vector. What does that mean? That means we want the horizontal component to be 0 and we want the vertical component to be 0. We don't want it thrown off. We need another force to balance off what happened with these guys. What do we need to do with that to get it back to 0? Here we go. Now, this is the main thing that we looked at, but keep in mind our resultant force was V plus W, which was 89.95I plus 5.80j. The equilibrium force, what we're calling the equilibrium force, is going to be also a vector, okay, that will bring it back to 0. It'll bring it back to center. It'll bring it that balance back. So what do you have to do? Since we want a 0, we want the equilibrium force to be 0 I plus, well, no. We want our outcome to be 0 I plus 0 j. So what do we need to do to get there? What do we need to add to this to get a horizontal component of 0 and a vertical component of 0? Well, we had a positive movement of 89.5. So to undo that, we would need a negative movement of 89.95 to get it back to 0. We had a positive movement of 5.80. We would need to undo that by a negative movement of 5.80 to bring it back to 0. Our equilibrium force needed would be negative 89.95 I minus 5.80 j to bring it back in, okay? That's what we're looking at. Lots of applications of vectors, especially those dealing with the jets. I don't know if any of you have ever flown or seen the equipment in a cockpit, or if you've ever been in a tower at an airport and seen any of that equipment. I've had a couple students in the past who actually worked with that equipment quite a bit. They said, oh yeah, they see vectors all the time dealing with speed. So those are a few things that deal with vectors. Make sure you try your homework. Give me a yell if you need me. And this is it. I hope you've had a great semester, and thank you all for all of your hard work. Talk to you later.